Okay, let's start. So now we're going to turn our focus to the feasibility problem of linear programs. We're going to tell you how to use the simplex method to detect feasibility or infeasibility. So suppose I have a linear program like this. Okay, all the constraints are less than or equal to constraints, I mean functional constraints, and all the right-hand side values are non-negative. Then we know finding a basic feasible solution for the standard form problem, okay, is trivial. Because to get the standard form, we need to add these slack variables. And we know for each constraint, the coefficient of the slack variable is 1, okay? And that's why you see this identity matrix as the coefficient of this slack vector, okay? So anyway, this is what we did starting from the first time we used the simplex method to solve problems. And we know what we actually did was to choose these slack variables to form a feasible basis and then start to change to other bases. Okay, that's what we did. So now the question is, what will happen if there are equality or greater than or equal to constraints? First, we will show you that this strategy does not work anymore, and then we will tell you how may we deal with that situation. So suppose I have this question, okay? Objective is not very important. When I have 4 variables with 3 functional constraints, there are greater than or equal to, equality, and less than or equal to constraints. According to the definition of standard form, suppose I get this. For the first constraint, I minus a surplus or slack variable. For the second constraint, I do nothing. And for the last constraint, I add a slack variable. Okay? And in this case, among these 6 variables, I need to select 3 to form a basis, right? And then I need to know whether that basis is feasible or not, according to the values of basic variables. And certainly now it is non-trivial to find one or to determine whether there is any basic feasible solution or feasible basis. Because no matter which 3 columns you choose, you need to really do an inverse of that basic matrix and then do a multiplication so that you may know the values of basic variables, right? There's no way for you to predict the values of the basic variables. So in this case, if I really ask you to find a feasible basis, there's no other way. All you can do is to completely enumerate all those possible combinations of 6 choose 3 variable combinations. Okay, so that's the difficulty we have in this situation with greater than or equal to and equality constraints, and we need to find a way to deal with that. There are multiple ways for doing that, and here I'm going to tell you just one, the two-phase implementation of the simplex method. This thing is one way of running the general simplex method. There are other ways for you to implement the simplex method, and here I only teach you this implementation. I hope you to understand that even though some textbook or some people say this is a two-phase method, actually this is not something that is different from the simplex method. Okay, they are not two different methods. The two-phase thing that you're going to see is just one way of running the simplex method or one way of implementing the simplex method. Okay, keep that in mind. It's one version of the simplex method. So suppose I want to find an initial basic feasible solution, or I want to show that nothing is there, then I may do this implementation in the following way. Suppose I give you a standard form linear program P, okay, like this, and then I may construct something I called a phase 1 linear program. Okay, in this implementation, I will do the problem in two phases. In the phase 1, I will construct another program like this. So first, there are standard form, there are equality constraints. For each of them, I add a variable. Okay, for each of them, I add a variable and make 1 as the coefficient. The reason for me to do that is very clear, because I want to construct an identity matrix in the coefficient matrix so that later I may choose all those new variables as my basic variables. I may choose them to form a basis. And that's why I say Q has a trivial basic feasible solution. All the original variables are 0. All the new variables are basic. Okay? And then I have an initial basic feasible solution. But then the question is, so what? Okay. We certainly have a way to solve the new problem with the simplex method because we have an initial basis. I mean initial feasible basis. But so what? Okay. The key idea is that we designed this objective function, the new objective function, in a smart way. The proposition here is that the program P will be feasible if and only if Q has an optimal solution in which all those new variables are 0. Okay, all those new variables are 0. Why? When I have a solution xy for the new program or the phase 1 program, okay, if there is any variable y that is positive, okay, that means the remaining x cannot satisfy ax equals b. Okay, whenever any y is positive or non-zero, that means the remaining x cannot satisfy ax equals b. Okay, because some y is still here, so it's impossible for you to see that ax is b because ax plus something is b. Okay, so if something is positive, then ax is not b. But if all those y are 0, then you know your x satisfies ax equals b. So the phase 1 program is determined so that you will try to minimize the sum of y. Okay, you will try to make all those new variables y become 0. Okay, according to this objective. So let's put it in this way. I give you an original program. I don't know whether there is any feasible solution that can satisfy this equality constraint while making all of them non-negative. Okay, then how about I construct a new solution, a new problem? For this one, I add some new variables, and I am asking whether it is possible to find something that is valid and that can have all those new variables 0. Okay, if that's possible, then the original problem is feasible. That's the idea. So if I can find an optimal solution like this, all the y's are 0, then the remaining part would be a basic feasible solution of P. Okay, it satisfies ax equals b, and also it will be non-negative because it is feasible for the phase 1 program, right? So then we can deal with the feasibility problem of the original program. One thing to keep in mind, even if in P the objective function is a maximization problem, Q will still be the same. When we construct Q, we completely abandoned the objective function of P because we only care about feasibility, right? In the phase 1 linear program, we construct this program because we want to detect feasibility or infeasibility of P. So it has nothing to do with the objective function. In any case, we would like to make all those new variables 0 So we will always minimize the sum of them. So some more details. After we solve Q, either we know that P is infeasible, or we have a basic feasible basis of P. Okay, if in Q the optimal solution has all the y's becoming 0, then it's good. We have a feasible basis. Otherwise, P would be infeasible. If we have a feasible basis, we will get back of the original objective function and then solve another phase 2 linear program. Actually, the phase 2 linear program is just the original program. You take the original objective function back. It's just that we need to do one tiny operation before we can really solve it. One key insight here is that phase 1 program is for we to get a feasible solution, and then in phase 2 we try to get an optimal solution. Phase 1 for feasibility, phase 2 for optimality. Okay. Regarding those added variables, we will call them artificial variables. They are called artificial because they are somewhat fake. Okay? They do not have any real or physical meanings in the original problem. They are created only because we want to check feasibility. So these artificial variables are definitely different from Slake variables. Okay? Slake variables have physical meanings that they are measuring the difference or the gap between the left hand side and the right hand side. Okay, they somehow tells you some physical things. But artificial variables, you don't need to interpret them because they do not mean anything. Okay, so two things to know before you really do the two-phase implementation. Previously, if you go back to see the previous slides, we say the constraints are ax plus iy equals b. Okay, for each constraint we add an artificial variable so that we can get an identity matrix. But actually we don't need to do that for less than or equal to constraints, because if you have less than or equal to constraints in your original program, then your Slake variable can serve as one column of the required identity matrix. Okay, so that means if you already have a variable that can be included in the trivial basis, which happens when you have these less than or equal to constraints, then you do not need to add artificial variables for them. We'll see examples later. So once we have this phase 2 linear program, we will then adjust the tableau to fit the initial basis. And then we just need to run the usual simplex method until we solve that problem. So let's see one example. So here, suppose I have a linear program like this. Okay, I have a greater than or equal to constraint which creates some difficulty. Then I will do the following thing to find or to try to find one basic feasible solution for this original program. So first, I will construct the phase 1 standard form linear program like this. Here, I will add 3 variables, right? 1, 2, and 3. The 2 variables x3 and x4, they are Slake variables. Okay? Because they appear in your usual standard form problems. For this, you need to subtract x3 from the left hand side. For the second row, you need to plus x4 at the left hand side, right? So they are Slake variables. They tell you what's happening in the original program. But for the last variable, x5 is artificial. Okay? And that's why in the objective function, you only see I want to minimize x5. I want to remove x5 from the basis of the phase 1 standard form program so that I have a solution that satisfies the original on 4 constraints. Here, I have 2 constraints, but I only add 1 slack variable. Because x4, even though it is a slack, it can be contained, it can be included in the trivial basis, right? Where is the trivial basis? Is here. Okay, I can use x4 and x5 as my initial basis for the phase 1 problem because I have an identity matrix here. Okay, so that will be what we're going to do now. We will use x4 and x5 as the basic variables to start our standard form, our simplex method. Okay, so we will prepare this tableau according to what we obtain as a phase 1 linear program. Okay, everything are copied into this tableau. And then you will see that this is not a valid tableau because of this particular number. For all the basic columns, okay, these 2 columns, the zeroth row should contain 0, always, right? This is a rule for us to maintaining those linear systems or any tableau. So if this number is non-zero, that somehow tells us that we have not completing the pivoting process, something like that. Okay, so before we run any iteration, we need to make sure that there is an identity matrix for the basic columns, and for the reduced cost, they are all 0. So we need to adjust the 0th row before we can run iterations. So we adjust the 0th row by adding row 1 to row 0. Okay, adding row 1 to row 0. We will get something like this as an adjustment. Now we have a valid initial tableau because here everything looks fine. So for this minimization problem, now we will start to minimize the objective value. Currently it's 6, and our goal is to make it 0. Okay, our goal is to remove x5 from our basis. Okay, and because this is a minimization problem, we're going to look for positive reduced cost. Oh, there are some possibilities, so then we will continue. The current basic feasible solution, okay, 00066. So this is an infeasible solution to the original linear program. Okay, original. What does that mean? This is certainly a solution, a feasible solution to the phase 1 program. But if we look at the 4 true or physical variables, this does not satisfy the standard form, the original standard form problem. Okay, so we need to somehow get rid of this x5 so that eventually we get a feasible solution. So now we want to solve this linear program according to this tableau, and we only need 1 iteration to take away x5. Okay, x1 enter, and immediately we can see x5 should leave. And then at that moment, okay, one technical thing we are doing is that we will remove the column for x5. Why? In this iteration, x5 leaves the basis, and in phase 1, if one artificial variable leaves the basis, it will never enter again because there is no reason for doing that, right? So if we see that an artificial variable leaves, we can take away that column to save some calculations. So certainly, if you are doing this by hand, then you may want to do that to save you some time. If you are implementing a program, implementing the simplex method or the 2-phase implementation, you will also do that, right? So that your program can run more efficiently. But anyway, that's optional. That only makes your calculation faster. But if you still want to keep this 5th column, it's up to you. But if I were you, I will take that away. Okay, so because in 1 iteration we removed all the artificial variable, we know the original LP is feasible. Okay, and a feasible basis is x1 and x4. Here, this is x1, this is x4. In this basic feasible solution, we can see that if x1 is 3 and x2 is 3, and x3 and x2 and x3 they are 0, then this can satisfy the original program, the original standard form program, and I have obtained a basic feasible solution. This can serve as the starting point for we to solve the original program. Okay, so a very quick summary. I have a program, and I do not have an initial basic feasible solution. So I construct another phase 1 program. After solving that phase 1 program, I either show that the original one is infeasible, or I either give you an initial basic feasible solution to start with. Okay, let's stop here. Thank you.